For me, a privilege to introduce Mr. Ronald Eguchi. I've been trying to get Ron here for a while, but due to conflicting schedules, he's a very busy guy. It just hasn't happened before. I encourage you to read Ron's bio that's posted online as well for the seminar. It's pretty extensive. I'm going to give you some highlights, but Ron is the president and CEO of ImageCat, which is a company that serves sort of in the disaster response phase for insurance agencies, NGOs, government agencies. And he's been at it for, I think, more than 40 years, it says here. It's been a while. And you can read all the accolades and awards, but things that I want to point out, there's a few things. He was appointed in 2023 to the California Governor's Advisory Board on Wildfire Technology Research and Development, and in 2024 as the founding chair of the National Institute of Building Sciences Lifeline Advisory Panel. He has authored more than 300 publications, many of them dealing with the seismic risk of the utility lifeline system and the use of remote sensing technology for disaster response. But my connection with Ron actually goes much deeper than that. Tony Vodacek, myself, and some folks from UB and Don McEwen were involved in an NSF project in what's called Partnerships for Innovation. And it's a very applied program at NSF. And we pitched the idea that we wanted to span the space between sensing technologists and disaster responders. In other words, we think we know what's possible sensing-wise, algorithm-wise, but we wanted to know from responders, what do they require? Because sometimes we overcook things here up in the academic ivory towers. You know, we think we can come up with all these wonderful algorithms, and an end user might say, I don't need them. You know, I literally just need a pinpoint of where someone was displaced during a disaster. So we cooked up this NSF proposal. It got funded, pretty large proposal. And Ron was on the advisory team from industry on that proposal. Then in 2010, the Haiti earthquake happened. I know some of you are probably maybe not too young, but it's pretty far back in our lives. But it was a disastrous event to the tune of hundreds of thousands of people dying. You know, it was a huge, tragic. And it was during the span of this NSF project. And I have to give Don McEwen, the co-inventor of the project, a lot of credit. Don and I shared an office over in the building 17, one of these adjacent open door offices. So we were partners in crime in a lot of our projects and budgets. And Don literally yelled at me from his office, why don't we fly WASP down in Haiti? WASP is our Wildfire Airborne Sensing Program. It's a shortwave, midwave, longwave thermal camera that we developed as part of a NASA appropriation award. Tony and Bob Kremens were instrumental in that development. And I, being who I am, I said, sure, Don. Don called Ron. Ron was in DC, he can tell you more. And I think by the end of the day, we had funding from the World Bank to deploy to Haiti to go fly WASP. And the intent was high resolution RGB imagery, mainly for building damage assessment. A huge network of engineers across the world were tasked to evaluate RAT imagery and other Google and even then pictometry imagery to do building damage assessment for the Haiti disaster. And the cool thing is I don't know how much if you can talk about that.
Well, you just about gave my whole talk.
Oh, sorry.
No, I'm kidding.
But it was really cool. A lot of the faculty and staff, NINA specifically, and other staff, the late Bob Kreisig, he was instrumental in helping us get the data that we couldn't download legally in a non-US territory. We had to download it in Puerto Rico. So Jason Follering, the flight engineer and system engineer, landed in Puerto Rico, and we had to pipe the data overnight. And then the folks here locally sprung into action, processed the data like, data need to be processed, and then released it by early morning of the next day, which was unheard of before. Google flew and actually FedExed their hard drives over to California on a daily basis. So they were probably a day or two behind RIT, the mighty Google themselves, which was a pretty big accomplishment for a university team. And many of you in the room helped make that happen. But prior to that was this man who actually got the funding for us to initiate the effort. So I want to say thank you again for that. And with that long introduction, I'm going to hand over to you.
Well, I want to thank you, Jan, because I was talking to Tony And Tony was trying to remind me that there was a pre-2010 meeting and discussion that led to, our collaboration in 2010. I said, I don't think so. I think it was, we had, because you and I had done some things afterwards. I said it's afterwards, but now that you mention all those things, now, I recall that, this is the value of collaborations, networking, doing, the sort of homework, to get to know each other and so forth, because trying to put an operation together to respond, within days, weeks of an event like Haiti was not very easy, especially, in fact, last night I went and looked at, my file on Haiti and what we did together. And there was a spreadsheet that I think was probably put together by RIT, and it had like 20 people all had some role in that particular event: publicity, data management, verification, validation, and so forth. And it was a big operation, and I really think that what came out of it were some real important milestones that changed the trajectory, of a lot of what we do in the disaster response area. So anyways, that's one of the things I'm going to talk about, and thanks for giving my talk. All right, so I'm going to say, well, first start off and say, thank you for all the meetings and visits that I had today. It was a real gauntlet. I think that the one break that I had, which was very pleasurable, was meeting for lunch with the PhD students and talking to them. I think it was Emmett that introduced me to the tradition, and I had a great time because I love coming to these sorts of things and getting to talk to students and throw to them that there's a lot of opportunities in the disaster area, especially if you have technologies that evolve and get better and that become more pervasive. In the sense that, used to be we'd have to wait 3 days before, the satellite would return. Now you've got things that are almost, near real time, and it's just a whole different and very large and robust set of sensors that are out there. Anyways, let me first tell you a little bit about me, something about me. So I gave a little bit of some introduction to the students, so forgive me for repeating some of the things. But I was born and raised in Los Angeles and had opportunities to move out, but I decided, I liked the weather and I liked the fact that my family was all in the area. So it was not a big, big decision or choice, with regard to that. There were a lot of things, that I remember and so forth. I know that I was the first one in my family to go to college. And, that was very important, for my family. And I thank my parents, for making that happen. My brothers and sisters, the sister, same sort of thing. I've always had this curiosity to create new things to try and make a difference. And so therefore, when I went to UCLA, I met up with in fact, I worked for a professor there who, was a real leader in the area of infrastructure, lifelines, how you take a systems perspective and how you understand the performance and how you can do things better. And I really appreciated, this notion of systems engineering and how you can essentially, take a much more broader, robust view of things, particularly communities and cities, so that you, begin to make, I think decisions that can affect, all aspects of the community, physical assets, socioeconomic factors and things like that. But I always knew I wanted to start my own company. So it just took me a long time to get to that point. But there was a point where I said to my wife, who had never worked a life, day in her life because she was taking care of the family and back then, generations allowed you to do that. So I said, I think now's the time to start a company. She kind of looks at me. I said, yeah, it'll just be 2 years. 2 years and we'll, sell the company, and then I'll retire. So anyways, this year we're celebrating our 24th anniversary. And my wife is not talking to me anymore. She doesn't, when I say something, she doesn't believe. But I think that, this whole process, it's been a journey, and it's included events, included people, things that are all very important, so when you guys begin to, start your career and develop it and nurture it, you're going to find that, people are going to be very important to help you get to where you want to go. And the more that you can interact and help them, I think the better off we'll all be. So I selected the title here, Communicating the Power of Earth Observation Technologies. And then I felt for this particular school, that idea, that theme, it's very appropriate. Earth observation, technologies, sensors, how you begin to assimilate all this information is very important. It's so important that I think that, I have here a picture is worth 1,000 actions, which is a play on, a picture is worth 1,000 words. And when you think about some of the decisions that first responders, that government agencies, even industry have to make after, some catastrophe, it's very hard. I'm a very visual person, so it's very hard, at least I think, to be able to capture the essence of what's happened by looking at a table or understanding, what is being produced or forecasted by an equation. It's really easy when you start looking at, images, looking at maps and things like that. And so that was one of the things that kind of attracted me to the remote sensing area. I'm sorry, what did I do?
Can you share the screen so the people at home can see?
Oh,
Thank you.
can you help me and
Oh, yeah.
let's do that? Because
Yeah, I can do it.
I'm sure I'm gonna screw it up.
Oh, you can, yeah.
So, that kind of brought me to, the area of, imagery. And for those of you in the audience who can't see my screens, and you guys can't see it. It was an image of Port-au-Prince, a very high resolution image. And, because it's so high resolution, we begin to look at it and think, there are a lot of things, that I see, but I didn't.
I'm gonna.
Well, I really screwed it up.
For Zoom, I always have to hunt for that little window that allows me to do stuff.
So that one, that's mine. No, back.
The small one.
First one, that's small, right there,
Max,
max,
yeah.
there you go. All right, now go down below,
Okay,
share
yeah.
screen, share screen.
Yeah.
There you go, and choose that screen.
I think I'm gonna sit down and watch. Anyway.
PowerPoint.
All right,
Quick question, sir.
yes,
With that image, is that a satellite image or a?
that was an aerial, I think it was an aerial photograph. Satellite images, you'll see some comparison and, big difference. And so when you begin to search, imagery for before and after comparisons, you're usually working with maybe Landsat or something, or even other, higher resolution satellites. And you compare it to the sorts of images that were being produced, by RIT. In fact, I remember Don sending me a big roll, which I still have on the wall of our office, of, for the trips. Yeah. And I really expect what that to people and say, this is, what, what we,
Three, first one.
Yeah, I'm glad I did that by email up there.
There you go.
Like, okay. All right. I'm gonna quit now. So, anyway, what really attracted me to, the notion that, a picture is worth 1,000 actions and so forth was seeing things like this, right? And, you see a lot of this. Here's Port-au-Prince. And you see the people of Port-au-Prince sending, us a message. They need help. So anyways, this kind of began, in earnest, I think, our relationship with our IT, and really sort of pivoting what people could expect, after a disaster. So I want to set the stage for, why this is so important, what we do with, industry, why we try to use what technologies, are available to better understand, what's happening out there. One thing is that 3% of the world's land surface is occupied by some urban settlement or environment. 3%. You say 3%, that's not really very much. I mean, but if you think about all the different continents, 3% is a very large, huge area. There are a lot of settlements, and CIS, who many of you probably know, has assessed that there were 75,000 very distinct urban settlements, and they can be very small, or they can be huge, like Tokyo. I was just in Japan 2 months ago. And it just amazes me, just how large these areas are. Maybe connected settlements and things like that. The other things that, this was back in 2012, but the size of urban areas was expected to triple by the end of this century, this decade. And that's, that's amazing. And you think about, risk being a function, both the hazard and exposure, we can see basically, because people are developing, areas are growing out, that this is increasing, the amount of risk that, we need to be concerned about. 44% of the population essentially live along the coast, right? That's a lot of people. And the reason why this is so problematic is that that's where a lot of our hazards are. The ring of fire, earthquake along, around the Pacific Ocean, tsunamis, coastal erosion, and now sea level rise. All these things are affecting these areas. And so as we grow and develop more along the coast, we're increasing the exposure and we're increasing the risk. So one of the things we really need to do is we need to think about, what's happening. And this is something that actually one of our clients, Aon Benfield, had put together in terms of tracking, losses from all natural hazards over a decade. And obviously it's going up, right? And it's going to continue to go up unless, we begin to think about this problem, in a more serious and I think a more impactful way. So one of the things people are thinking about right now is the notion of resilience. So how many of you have used the word resilience in the context of a natural disaster hazard? Okay, all the old guys. Okay, some young ones, excellent. All right, resilience, is a term that, a lot of people define very differently, right? So I asked my granddaughter, who was 4 years old at the time, said, what do you think resilience means? And she says, oh, Grandpa, I think it's when somebody gives you something and takes it away. When you think about it, that's, could be, that's very accurate because you have cities that are built. And then Mother Nature comes and, and takes it away, destroys it, and so forth. That was pretty good. I happen to use it more scientifically. And the notion of resilience actually is a function of, what we call the 4 Rs. And I'll talk about those 4 Rs in a bit. But the idea is that, you have community, essentially community activities, existence, before an event function at, let's say 800%. Then what happens is that you have an event where, that functionality and activity drops immensely. And it drops depending upon how robust your community is. In other words, how well have you designed your buildings? How well have you constructed your infrastructure and so forth? If it's very well designed, then it's not going to fall too far. But, a lot of times it falls, very significantly. Rapidity is the notion of how quickly can you repair or restore an asset. So, for example, I'm very involved. In fact, the introduction talked about my experience with lifelines. And lifelines, really are defined not so much by the amount of damage that they sustain, but more by, how long they are out from the disruption, the outage period. Okay. So rapidity means, how quickly can you bring your system back? Can you bring it back because you put more people in the field to make repairs? Is it because you find the damage and the breaks, say, to a pipeline more quickly? So it's a lot of things that I think technology could help with. Resourcefulness and redundancy are factors that, really kind of characterize a community's ability to kind of pull together, to be resourceful, be creative in terms of how you sort of allocate resources and so forth. And redundancy is that the more you can have redundancy within, a community, whether it's lifelines or what, the more likely that you're going to be able to either recover or continue to operate after the event. So the 4 Rs are very important. And I was talking to somebody about a paper that I had written or participated in. That the number of citations on this is enormous, and it's because it provided a very simple, but I think very not standard, but a good framework for how you begin to understand, how you begin to monitor, how you begin to measure resilience. Right. So this is kind of what I want to discuss today. And what I want to emphasize is the role that Earth observation technologies can play in enhancing resilience. And the 3 areas that I'm going to talk about, and no surprise here, I'm going to talk about the Haiti earthquake in 2010, and from the point of view of rapid damage assessment, and the notion of crowdsourcing, at that time was very, very immature. So I wanted to, discuss a little bit more about that. Second area is recovery. The different phases of disaster, preparedness, response, mitigation, recovery. Recovery is probably the one phase that is the either hardest or least understood. Okay, because there's so many factors that really affect, that aspect. But I'm going to talk about something that we did during Hurricane Charley. And then my final discussion will be on exposure model development. And this is something that, there's been a lot of research done on this and so forth. And I'm going to talk about it from the perspective from an insurance company wanting to understand you know, where the risk lies with regard to properties that they either insure or they have reinsured, or maybe there may be an investment, and how remote sensing, you know, can help with that area. So these are the three areas that I'm going to cover today. So I'm going to end at fourth, right, and then fourth. Okay. All right, so I'll start with the Haiti earthquake, and I think this is probably very early, probably satellite image, and you know it's a part of you know, Port-au-Prince, and I always say that the Haiti earthquake, it was a, you know, the earthquake itself was a major one, but it was not catastrophic in 1907. Like, you know, here in the US, the magnitude 7 would be something that would cause a lot of damage, okay, but it wouldn't, you know, level the whole city. But the impacts that resulted from that magnitude 7 earthquake in Haiti were enormous, tragic, you know, as we discussed. Over 200,000 people killed. You know, they still haven't rebuilt a lot of areas, and look what's happening, you know, now, the political chaos and so forth. So there are a lot of factors, you know, that play into how quickly our community can recover. So when here's the post image, and it's either your image or Google's image, but you can see the real value and benefit of the before and after. Being able to contrast this was very important in having, you know, our team and others determine which buildings, you know, were collapsed, which ones were heavily damaged. And we had a lot of great partners here. We did the work for the World Bank, for the GFDRR, which is an element or component of the World Bank, and our partner in this was RIT. So the crowd, the notion of crowdsourcing at the time, it's just 2010, you know, and there was, you know, there was thinking crowdsourcing, you know, could be used for, you know, a lot of things, but nobody ever thought about using crowdsourcing to do damage detection in a large disaster. And this is what we, you know, we have actually done a pilot study in China with one of the professional organizations that was very key. In fact, it was EERI that, you know, we had kind of pilot tested. So when the Haiti earthquake occurred, we thought, why not? Why not try to see if we can use this event to test out and evaluate, you know, crowdsourcing as a, you know, as a technique methodology, using, you know, the best imagery that we could get. And one of the things that came out of this was the, because we issued a, basically an alert, you know, through EERI that said, you know, if you're interested in helping the people of Haiti and so forth, why don't you register, become a, you know, you know, damaged, you know, inspector, you know, using remote sensing data. And what we'll do is we'll check out grids, you know, to you, and you would do an analysis and send it back. So over 600 people from 23 different countries. This is the individuals from, you know, these universities participating. So pretty impressive all over the world. Government and nonprofits that were involved with this effort. There were 17, and private companies also wanted to be involved with this. So these 600 scientists and engineers helped form what we called GeoCam, and that was the Global Earth Observation Catastrophe Assessment Network. And using GeoCam, we were able to do this very rapid damage assessment. So one of the things that we had to settle on was how we were going to sort of measure or quantify damage. And so of any earthquake folks here? Familiar with earthquakes now? So there's a scale that is an international scale, it's called the EMS, European macroseismic scale 98, that we use, which is primarily for field surveys. So if you look at this, you know, you can see here's a building. If you went in the field, if it looked like this, you would say, you know, no damage. And as you go up, you know, it had different grades. So we felt that that would be a good scale to start with, but we wanted to transform it into a scale that remote sensing, you know, could be applied to. So, you know, I'll show you some other examples of these things here, but that was, you know, that was a good decision for us to make, but it did point out at the end that, you know, there really needs to be a damage scale that is based, you know, exclusively on, you know, remote sensing data. You can't just do it based on what you see in the field. And the reason is this. Trying to interpret damage for lower damage states. So if you think about 3s and 4s and 5s, it's very, very difficult when you just have images that show you the top of the building. Okay? Here's an example. Here's a grade 5, which is complete collapse. Okay? You don't need field survey, you don't need anything, you know, elaborate to see from the air or the, you know, ground. This building has collapsed, right? So we knew when we did our analysis, when we had the crowd help, that we're going to have a pretty, you know, like very high probability we're going to be correct when, you know, when people had rated something as grade 5, that is, probably that's the case. But if you look at some of the other ones, here's a grade 4, a very heavy damage. You might be able to make that assessment from the air by seeing the debris around the side. Okay, but you know, if you look at the roof there, maybe the roof looks okay. Don't know. But here's one, grade 3, where you have substantial to heavy damage. But, you know, structural engineer would look at that and say, you know, this building needs to be torn down because number one, there's some, you know, cracks in the column and it's not straight. Broken, you know, it's bleeding. Okay. So how do you tell from the air that that would be a grade 3? Okay. So one of the things that the World Bank needed information for was they needed to know what the full extent of damage was to all buildings, not just to the ones that had collapsed. And so one of the things that we decided to do in lieu of being able to look at things like pictometry, which gives you sort of an altimeter or view of these buildings, is to conduct field surveys where, you know, we actually identified blocks, a number of these, where we had engineers go around and they would say, you know, this is grade 5, this is grade 4, this is grade 3, you know, and so forth. And that information, you know, was collected and we created these sort of histograms, you know, for all the different damage states for different types of development here, commercial, downtown, industrial, residential, and so forth. What this did was it gave us a way to scale all the accurate data we thought we had on collapsed structures down to lower damage states. Okay, and when we tested it out in, you know, other areas and so forth, you know, it was reasonable, considering, you know, the crudeness of the scale anyway. So that was one of the innovations that I think came out of, you know, the work that we did. And it was, you know, we had to think about how we're going to be, you know, more encompassing there. I'm going to digress a little bit more before I get back to the crowd, which is, you know, the whole purpose of that segment there. But so the other thing we realized is that, you know, the determination of damage levels is very crude and very subjective. So how do we, and this is afterwards, how do we create something that is a little bit more systematic, that would ensure more consistency, that would allow us to come up with a better indication of whether, you know, we have minor, moderate, or major, you know, damage and so forth. So we came up with this idea of what things can you actually see? What can you see from, you know, the air? One thing you can see is you can see debris. Okay, now debris just doesn't come up from the ground, right? It comes because you have some sort of failure, walls have, you know, come out and so forth, and it could be various degrees. You can also see things on the roof. Okay, so here you've got you know, obvious damage to the roof. Here maybe part of it's missing, and so forth. So roof damage, what's happened to the roof, is another indication, you know, that you've had some serious damage. You can also look at things like, you know, wall damage, you know, either through the debris, maybe you've got a pictometry image, or in some cases, are you guys familiar with pancaking buildings, right? You got these, you know, multi-story buildings, and a lot of times you've got a soft story. Soft story is, you know, you don't have kind of walls, it's columns, and it's very weak relative to things that are above it. And so you get collapse clip. And what you see, if you see one of these in an aerial image, you know, it just progresses. You can see actually it's stepping, you know, down to the various floors. So that's another thing you can look at. And then you've got pounding. You know, a lot of these places, even like in San Francisco, the buildings are right next to each other, okay? And they're different heights. So you can't expect the buildings to all sort of sway together, you know, different heights result in different responses. And so you get buildings that are clashing together like that. And in cases, you can see where, you know, that sort of pounding, you know, has resulted in, you know, buildings maybe next to it, you know, collapsing and failing. So a lot of things here that we think you can see and use and interpret in, you know, damage to a building that is much more quantitative. So one of the things that we've done is we have tried to create these kind of major blocks of how you describe damage. We've looked at how you describe various levels. So for example, could be things like roof damage where significant damage, certain percentage of the roof has collapsed, you know, all the way down to minor, where you just see minor cracking. So all these things, you know, I think are things that you can again see and quantify. And what we did is we collected information from the field. We took the GeoCat observations, and then we also did something much more, you know, specific for some buildings, and created what we thought were, you know, good assessments of weights to apply under each of these categories, so that if you began to click off, for example, you know, this is major roof damage or whatever, you would come up with a number that you would be able to compare. Then you enter some sort of scale, and there we would get a better assessment of whether, you know, it's a grade 4 or 5 and so forth, as opposed to having, you know, just maybe one person look at this. So anyways, we thought this was a major innovation that we developed actually way after Haiti, and it was more for Europe. There was an insurance entity that wanted, not only for earthquake but for flood, some better way of assessing damage using remote sensing data. The scale. Okay, so back to the crowd. What did we have the crowd do? We asked the crowd to do two things. Tell us which buildings you think had collapsed or had severe damage. Just those two. We wouldn't want to ask them, you know, minor damage or whatever. It would be unreliable. Those two, that. Then we asked them to delineate the building that they looked at. Draw a, boundary around it. And can anybody guess why that was important to the World Bank? Footprint?
Training data?
I'm sorry?
Training data?
Yeah, could be, but no. These are all like 2 to 3 story buildings, so if you knew the number of stories, you had the footprint, you could compute the floor area, the total floor area that needed to be replaced. And so, as you'll see, we were able to use that in calculating what the repair costs would be, for, footprints and for other areas outside. So anyways, when we started this, my company, we're not a very large company, but we work very hard and very efficiently. So in the first several days, my staff and engineers and so forth were able to come up with 576 delineations in the time that we worked, which is like 2 or 3 days. And this is the area that we started off with. So the next day, 22nd, that's when we brought in the crowd. If you look at that, this is each day. It was just amazing, when we started getting in the information and data to actually see, how rapid we were able to, to get this information and to have this information collected, and then being processed, to help assess, what the repair costs, were. So this is the way the total floor area, was distributed along the damage grade scales, the different development types. This is what, calculated the number of buildings in those categories. We knew it was either 2 or 3 stories. We calculated the floor area for the building, and then we basically summed it up for all the buildings in that category. And this is what we came up with. When using cost numbers to indicate the cost to repair a building that was, say, grade 5 damage versus 3 versus 1, we use these values, which is what the bank told us to use. And then for each grade, we totaled up the total number, or this is the dollar value that so it's $1 million. That's pretty cheap. So anyways, this is where we ended up. Total floor area of about 12 million square meters. Loss we calculated at $2.2 billion, which doesn't sound like a lot, but it was like a third of their GDP. Big part. Okay, so I'm gonna pause right here for just a second, see if there are any questions before I move on to the next one. Yeah.
What's the point of having category 5 and 4 if the return cost is identical?
It's they did probably not much, but the actual cost is associated with not repairing, just building a whole new building. So whether it's severely damaged or collapsed, it's the same cost. Any other questions?
I might mention quickly, just as a tag before Ron moves on to the next topic. So Dave Messenger wrote one of his students wrote a nice algorithm to do just an Novus distance classifier. The World Bank handed out these blue tarps, or the relief organization. So Dave could actually locate and pinpoint, pin drop all the displaced refugees, so they could actually respond and provide relief. And then an Air Force student, Rick Labia, used LiDAR. And he basically facetized the LiDAR point cloud and then just calculate normals to each facet. And based on how the normals were distributed, you could sort of assess the damage in the building. The normals, like on your roof, they will all point right in the same direction on one side, but the same direction on the other side. But if there's scrumbling, all those normal vectors will point all over. And so you could use LiDAR to also do sort of severe damage assessment. That's pretty interesting spin-offs to that project, I think.
There were a whole bunch of things that, we can't necessarily write about, but we were at one point thinking about, rather than rebuilding, for the fence, move it. To an area where, you're gonna have to rebuild the whole city anyway, why don't you make the infrastructure all, more resilient to things? And so they were actually, thinking about an area which I can't disclose, but to rebuild. And the other thing is that, a lot of people are being resettled in areas that were in floodplains. And so, Haiti is hurricane, and the hurricane season was coming up. And so, that was another concern that they had. Okay, let me go through these really quickly. So Hurricane Charlie, this is my recovery example, was a Cat 4 hurricane that went through the western portion of Florida. And in fact, it's funny because, a number of years later, I think it was 14 years later, Hurricane Irma came basically with the same track. And so, this is where you wonder, okay, was the preparation, that was made after, Hurricane Charlie, did any of that actually have an impact? So that's one of what we didn't study that, but that would be one of the questions that I would have. So our partners here in crime included University of Memphis, UBC. Somebody would say UBC, right? You went to UBC, no. Somebody went to UBC. And then University of Delaware, we all worked together on the Senate and the SPECTRA. So we said that remote sensing can do a couple things in terms of monitoring recovery. It could be, you can look at debris removal as a indicator, the rate of rebuilding, and then you can also see whether businesses, whether there are cars in parking lots and things, whether that is active or not to make an assessment of whether there's been some sort of recovery. The area that we selected was Punta Gorda, which is a retirement community. It's a mix of residential, commercial. And the thing is that they had a lot of prefab housing there that, with the major hurricane effect not being water, but wind, these buildings were not very resilient to severe winds. So here's an example of a prefab park area. It was several months before the hurricane. The hurricane came along, essentially destroyed and demolished, a lot of the structures. You could still, this area here, this was actually a car dealership, okay, but residential and so forth destroyed. Now we use these three parameters: debris present, housing repaired or rebuilt, and this is operating as part of our metric for determining recovery. And after a little over a year, 2006, if you looked at the image, basically what you had were not rebuilt buildings, but you had trailers that FEMA had brought in for residents, that had been essentially couldn't live in the houses. This is 2008, 4 years later. You see the trailers gone, you still see debris present. The car dealership is still there. Look at 10 years down the line, you see that everything's been cleared out. And if you look at 12 years, you see a new development being built, not new prefab houses in the same footprints, but it's more of a community resident situation. And finally, after 13 years, it's been rebuilt. So 13 years afterwards, I mean, is that acceptable? Certainly if you're one of the occupants, residents that were affected, would not. But we need to find ways to be able to measure, so we can understand, measure recovery, so we can understand what sort of things, might sort of accelerate or impact things on a more larger, citywide basis. So one of the things we did with NSF is that they gave us a 5-year or a grant to look over 5 years on, what sort of recovery has occurred, to Punta Gorda. And it turns out that we selected an area that, you know, 6,000 buildings, you know, were, part of the survey. And the reason why we select those buildings is because we were actually given access to the building permit data, which discuss, you know, basically at certain intervals, you know, what was being done to essentially rebuild, you know, these buildings. So what I'll point to here is this green area here, and this is our attempt at trying to define a series of measures and metrics to define recovery. Okay, and you'll see in this next slide here, they include things like whether, you know, the building's been demolished, whether it's been rebuilt, repaired, and so forth. So these are all things that we try to observe either from the building permit data or from the imagery and do a comparison, you know, to see, you know, how well, you know, the imagery was doing relative to actual field information that was being collected by the city. So we had building permit data on a 3-month basis for essentially 4 years. And this is what, you know, the information they had actually collected. The remote sensing data focused on these things. You know, it didn't have the interior because you can't see inside, you know, buildings. But we collected, we did this analysis on an annual or yearly basis. Okay, so if you did a comparison between, you know, 12 months remote sensing and 12 months, you know, the building permit data, you see that essentially most or a lot of buildings have been repaired. There was a lot of under construction and so forth. And then 2 years afterwards, you see that, you know, large portions have been repaired and it's very little left to, you know, to repair. So, you know, what we're trying to do here was at least create the basis, you know, the foundation for developing a scale where you can begin to use, you know, remote sensing and know that it's tied to these sorts of things like, you know, building permit data and so forth to measure essentially the recovery rate of the community. Okay, last pause before I go to the last phase. Any questions? Yeah.
Do you contact the local city or local government to
Well,
get so in this process?
Yeah.
Did you contact the
Oh,
local,
yeah.
the local government to get the, you must have some documentation.
Yeah, absolutely. They're a partner.
How do you use that?
Well, the building permit data, we wouldn't have been able to get unless we actually had an agreement with the city. So we have that information and we actually conducted several, I forget what our social scientists call it, the campaigns within the community to get their opinion on things like, you know, is recovery proceeding, you know, the way it's proceeding is acceptable or not. And you know, you would find that, you know, there are a lot of critical comments that were made. It wasn't moving as fast as they liked. So, and there was one other one. Yeah.
Did you look at any data before the hurricane itself, like how long it took to reach some kind of normalcy?
No, that's a good question. You know, maybe that's how long it takes anyway. Who knows? No, we that would have been a good baseline, you know, comparison. And to tell you the truth, I was the PI, but I did none of the work. So they may have done some of that, but you know, I don't know. But you know, the normalization, I think, is very important. And these are very smart people, so I'm assuming they did something. Okay, I'm gonna look. Yes.
Yeah, one more. Was there any spatial analysis? Like, I noticed that there's some areas of mangroves, for example, always they're presented as being providing some resilience and some natural resilience, things like that. Did you do any spatial analysis of where damage and
No.
recovery?
No, you could have selected a number of areas, and we selected Punta Gorda largely because you know, had the ability to work with the building officials. It was probably one of the areas that was more severely impacted. You know, again, this was a sort of pilot study, even though we had 4 years to do it. You know, we didn't get, the budget was not very large either, but, yeah. Yes,
Feel free to defer this question.
Yeah,
we
John.
will address it, but I'm curious, what the impact of the more recent commercial transformations have had on the business and the type of work that you do. And I'm thinking of daily observations by planet, the emerging synthetic aperture radar observations, which are very frequent. How has that changed, or will it change the work that you're doing?
I think it will, you know, I think I explained to you, I believe, or that our company does no post-disaster reconnaissance work anymore, because it's very competitive and a lot of the information FEMA tends to release, you know, for free. You know, so our insurance clients will also always say, yeah, I can get that stuff from FEMA. But I think it does help because you have multiple views of something. You maybe have, you know, more consistent time-wise views. What's important is resolution. The planet stuff, you know, is still pretty coarse. You know, it's nothing like anything RIT has collected. So if you're just looking at some sort of course assessment, it's probably very valuable because you're trading off resolution, granularity with timing. So, but I still like airplanes. You know, you can fly them anywhere, anytime. Okay, I'm going to finish this up real quickly. So the last one is building inventories, exposure models, and the point that I always make is one size doesn't fit all. You know, it's not like one resolution, you know, is applicable in all areas. You know, if you look at things on a global scale, the resolution could be, you know, Landsat data, whatever. But as you begin to move up, you know, from global to country to neighborhood to building, you know, you really need to increase the not only the resolution, but a lot of the spectral bands and things, you know, to give you a better sense, you know, of how you characterize a particular asset. And so, and you know, even with all that, you still have to use engineering judgment, you know, to determine what all that means in terms of, you know, fragility or vulnerability. So I picked the Tianjin for a number of reasons. There was a major explosion and fire in 2015, I believe, in the port of Tianjin, so it brought attention, you know, to this area. But I want to make a couple points. First point is that this is 2002. This is Tianjin, at least in the area within there. This is 2015. It's the same area. I'll go back. Okay. So if you're an analyst, say an insurance company, or you're an analyst trying to make some assessment of what your risk would be over the next 10, 15 years and so forth, and you're working with a situation like this where the exposure changes so rapidly. This is where remote sensing becomes very important, because, you know, you don't have to go out and do, you know, building surveys, you know, by sending, you know, maybe Google out, you know, with its, you know, cars and things like that. It would be very expensive and, you know, very cost prohibitive. So, you know, remote sensing, I think, offers, you know, a very, very effective way to begin to characterize, you know, exposure in ways that it would help you, again, quantify vulnerability. How many buildings, what type of buildings? If you do stratified sampling, you know, you can essentially apply that to come up with, again, inventories and profiles of cities, you know, based on merging the imagery, again, with, you know, sampling, field sampling. Now, the other reason why, it's, that I wanted to point out here is that a lot of times when you are trying to ensure a portfolio of properties in a particular area where the data is not very readily available. You know, sometimes what you do is they tell you that the total insured value of the assets is, you know, maybe $100 million. And where they place those assets is at a sanctuary in the city. Okay, now, you know, for some hazards, maybe like earthquakes, which is, you know, very widespread. You know, maybe that's okay if you're looking at, you know, again, globally. But if you're looking at floods, if you look at anything which has a more localized effect, there ain't no way that that's going to be adequate. So one of the things that we've used remote sensing for is to begin to sort of parse out and look at the homogeneity of areas and so forth, and begin to assign classifications to these various areas. So for example, here, all the green areas are rural, the yellow areas residential, more highly urbanized areas are going from orange to red to purple, to more high rise. And the industrial areas are in blue. So now you have some sense of how, you know, the different development types, they are being essentially located, you know, within a large area. Now, if you are able to associate, in this case here, what is important is the notion of, well, these things here are total insured values. It's what, you know, the insurance company has on the books in terms of the value of assets. And this happens to be more sort of industrial things. So this is an actual client. And so as you begin to sort of drill down, you can see that that total insured value, which happened to be maybe at one point, really does vary, you know, across a very broad area. So rather than being right there, okay, you got a distribution, geographic distribution like this. Here's a flood hazard. Okay. So there are a lot of areas, the darker the shade, you know, the more severe the flood hazard is in terms of, you know, potential flood depth. A lot of areas are in the flood area, prone area. A lot are, you know, or some are not, so forth. So now they have at least the means of looking at the total, the number, the value in different flood depths, flood areas. So they can take, you know, flood damage and fragility models, take the insured value, and they can make some assessment and forecast out what the projected losses might be on an annual, maybe 10-year, maybe 50-year basis. And so it gives a much better way, you know, for them to understand, you know, whether high risk or low risk, and also whether, you know, these properties, a lot of times, if they're all sort of accumulated in one area, you know, you have an event that hits that one area, and then you get big. Whereas they like to spread things out so that, you know, if there's an event, it only affects part of that portfolio. Okay, so anyways, getting back to the original part of the story, you know, losses are going up. But if we can become a lot more intelligent and smarter about how we, you know, measure resilience, how we invest in resilience, you know, perhaps this curve here begins to, you know, trend in the other direction. Okay. So anyways, I want to acknowledge, you know, our sponsors and our partners, you know, if there are any questions, I'd be happy to answer. So anyways, thanks.
There have been some questions in between, but any other questions for Ron?
More of a logistic question, like, you know, you guys are assessing again, and let's say, you know, came up with a number like $2.2 billion. What's the range of error that they does it, I'm sure people care when it comes to.
It could be very large, you know,
Yeah.
it could be maybe 50% on each side, you know, maybe in certain cases 100%. But, you know, the thing is that, you know, when these, whoever the entity is trying to make a decision, you know, they don't have, sometimes they don't have any.
Any other questions? I think one thing that struck me in working with that NSF project and with Ron and others, and now eventually farmers were, you know, that need for applied thinking. And we often do blue sky research, you know, the stuff that we enjoy and want to pursue. But I think this really hit down to me in terms of what do people on the ground need. And it's often not fancy algorithms and fancy solutions we think we can come up with, but rather things that are really pragmatic and required on a daily basis. And that's the Air Force students actually told me that, what did he say, that a good solution today is better than a perfect solution a week from now. You know, that kind of thinking of this disaster response seemed to resonate really well, you know, as it's coming up with those building damage assessments, displaced people, things like that. Quickly, even if you have a very large error bound, is much better for the decision maker than saying, sure, I'll give you that perfect solution a month from now, then the response time doesn't happen. So Ron, thank you really for visiting, and I'm glad we finally got you here. And yeah, well, I believe there's some cookies and coffee outside for those who want to visit some more. So thanks again.
All right, thank you.
Well,